Hey, so today what we're going to talk about one of my favorite topics really just about ever. It's kind of the long view, material science, how it fits into history, how technology, science, and history all kind of fit together. And that's what it's all about. Just test my pen. Doesn't work quite the way I thought. Now it should work. So what I want to do with this is, first of all, last time we talked about what materials properties are. We're going to build on that. We're going to talk about how the materials available over time have changed and put that into properties, talk about new properties that are available. Really, properties enable us to make cool new stuff. That's what we're going to talk about. That stuff makes the human experience better. It makes us live longer, makes our lives richer, all of that. And what we want to do is we want to train your kids to be scientists and engineers. So we're going to talk about how we can do that quantitatively and look at things in a different way over really broad scopes of history. And then hopefully we want to see how this applies to their life. That's really the whole idea of what we want to do with all of this stuff. And so let's start with something that people might know something about. Pick a couple fun examples. Skis being the first one. Skis have been around for a long time, since the 1500s and before. Great way to get around snow, like it might be in Ohio right now. Back even in the day when I was a kid, maybe a little not little bit before then, my grandparents' time certainly, skis pretty much looked like this. Wooden blocks might be carved. You might put a little piece of twine on here, pull the tip back so it doesn't dig in. Your bindings would be very primitive, very simple. Everything has really changed. If you go to the sporting goods store today, they will happily relieve you of several $1,000s and give you something really high tech, but it is much better. You've got steel edges, you've got an advanced polymer base, you've got a foam core to minimize weight. Moving the base and the top apart actually gives you control of stiffness is an important thing you want to do. All of this has gotten better. Manufacturing techniques come in, and then there might even be some other piezoelectric sensors or dampers that fit in here that again make the experience even better than it was before. So skis are a great example of how materials have evolved to move forward. Another one is canoes. Back in the day, we had our Native Americans riding around, trapping beavers, fishing and all that using canoes like this. They made out of bark and fashioned twine and all that. This was what people's livelihoods were dependent on, being able to get across the water in these things that were leaky, heavy, crummy. Now, ordinary people can go out and buy a Kevlar canoe, Kevlar fiber, epoxy. The canoe might weigh about 30 pounds. They're affordable. You can use them for fun. Again, an example of how things have gotten better, enabled by materials, design, all these kind of good things that end up making our lives better. Another one that's kind of in the fun category. Back in the day, Edison made the first photographs. Materials was key to this. We had a wax cylinder that sat there. You'd speak into this. That would cause little scratches in the wax, little wiggles based on your voice. There's a little diaphragm in there, another interesting bit of material that would cause that wiggling. Then when you'd spin this thing, go back in the same grooves, and your voice would come back out. Back in the 1880s, that was the best way to do it. Back in the day, I thought I was really cool as we're coming out of the 80s to the 90s. We had these things called compact discs where we could basically store digital information, make little pockmarks in aluminum, and that would allow us to store music. And if we had a lot of music, you might have 200 albums. Each of these is an album, had a bunch of songs on it. Remember albums? Those could go into something like this. This is a thing that would hold about 200 of these. These were just about as cool as it was back in 1990. That's how you'd carry 200 albums around. Now you can get an iPod Nano, for example. This has been around since about 2010, about 5 years. You could put those 200 albums on something that fits in your pocket very easily. Again, material science, there's a lot of silicon memory technology, there's screen technology, capacitance sensors, displays. All of that and the processes to put that together have been relatively recent and a big deal. It makes our lives better. Again, in fun, sports, rich man sports, yachting. The very first America's Cup, always been a very rich man's game. The very first boats that this was done with were the best that you could afford at the time. These might do something on the order of about 8 miles per hour. If you spend all the money you have, you could do that, and the Americans won the first one in 1851. One of the greatest comebacks in sports was just a couple years ago, 2013, when Team Oracle set the rules, and a few teams built these beasts that were extremely light, based on big carbon fiber wings, carbon fiber little hydrofoils that sit beneath this. And these can do about 50 miles an hour, 45 miles an hour or so on 20 mile an hour of wind. Just go like mad. And the key is making these things really light, really strong, so that they're light enough so they can get up on these onto these hydroplanes and just go. Again, vehicles that can carry 10 people around just using ambient air, 50 miles an hour. Pretty cool. Pretty interesting ideas on how sustainability might come if we can scale something like that up. Again, materials are key to that. Design, all kinds of other cleverness is also important in that. So we kind of take the long view. Consider about 8 generations ago, 1800 versus 2000. Life expectancy back in 1800, you'd be lucky to make it about 25 years. Today, if you're born 80 years ago, you can expect to be alive. Done much better, and it's thought that kids born today might have a shot at living 150, 200 years. Who knows? Back in those days, maybe you could make in today's dollars, if you were really lucky, something like $2,500 a year. Food was simple, furniture was simple. Healthcare was kind of non-existent. Today, your real income, in today's dollars, might be, on the order of $50K a year. Some better, some a little worse. And the things you can buy with that are things that weren't even available back then. So things have really changed for the better. Again, I think it's technical developments that are a big part of that. We like showing data. Here's life expectancy versus year. This is a linear plot. Just going 200 years is difficult. What if we want to go back to caveman days? We'll consider that. But again, you can see we go from 20 to 30 years life expectancy in developed and developing nations now. Better in both places. Developed nations doing better. Again, data is a good thing. We're a little bit limited, that we often like to look at these data in linear scales, and I'll talk about the limitations of that in a little bit. So we can go on and on with this. There's all kinds of great examples you could use with your students examples of how materials have changed the world. Medical devices, prosthetics look completely different. Personal transportation has different materials. Look at the Model Ts versus today. There was a lot of wood back then, a lot of very heavy stuff. We're really trying to lightweight cars. Aircraft have changed. We've gone from aluminum vehicles lately to aluminum airplanes to those that are made of composites, much like that America's Cup boat that I showed you. Food packaging, we've gone from mason jars to little Capri Sun pouches. Buildings and roads haven't changed too much. I think there's revolutions coming there. Sporting goods, huge changes in football helmets, hockey gear, all that kind of stuff. Musical instruments, I think, are a little bit behind. I predict revolutions coming up in that. Stradivarius guitars are neat, or violins are neat, but there's a lot you can do today. Art, if you're doing studio art, materials is an important part of that. Military stuff, armor, all that changed dramatically in the last days. So what makes next generation stuff? I think there's really 3 parts of it. The first part of this, you need an idea. And this is what we call design. And if you're going to make a really high efficiency, lightweight engine, you'd use really high temperature, really lightweight materials. For example, you could say, I'm going to make an engine out of diamond. Be an interesting idea. So the second thing you might have is a material that enables that. That's number 2. And then the third thing you really need is manufacturing and process. Forgive the handwriting, but I think this is really kind of what's going from easy to hard in a sense, because it's easy to have an idea. It's easy to put out a design and say, boy, if I'd like to make something, if I could just make this thing super thin, I could make it this strong. But getting that material that's that strong and that thin is a problem. So you have a problem getting the material, and even if you have that, example, you have a diamond engine, how do you turn a diamond into a shape that could accommodate an automotive engine? So this is, part of my motivation for doing these things. I think we overemphasize the ideas and we underemphasize the hard parts. And there's a lot of people that have put careers into how we make stuff, how we shape materials. It's really important stuff. It's important to our gross national product and our way of life. So let's spend some time focused on the hard stuff. Okay, so I'm going to come back to those themes. But what I want to do first is put a little quantitative basis behind all of this and think about two ways of thinking. The graph I showed you before was linear. I also want to think about logarithmic thinking. This allows us to compare very different scales. We consider things that are very different, like how cavemen were versus how we are today. And I'm going to link two things primarily, really length scales and time scales. I'll also show some properties on a logarithmic scale in a little bit. And linking length scales and time scales is really the key of material science. We deal with atoms that are unimaginably small, and we turn them into things that are, bridges and houses and all these things that are very large. We have to bring those length scales together. Also, as atoms are vibrating at remarkably high speeds, high frequencies, and that turns also into some properties. And linking those length scales is difficult, and we need logarithmic thinking to do that. So I want to introduce you to logarithms. Most of you have probably seen this before, but let's consider numbers. 1, 10, 100, 1,000, 10,000, 100,000, a million. What's the pattern there? Well, each of these is basically, we're going 10x from here to there, 10x from there to there, 10x each time. So the other thing we can do is do a logarithm of these things. And we can say, okay, what's the number of zeros on these? It's basically the logarithm. Well, 1, there's no zeros because that the logarithm 0. 10, there's 1 0. 100, there's 2. 1,000, there's 3. 10,000, there's 4. 100,000, there's 5. Million, there's 6. And I could do this the other way too and go back to 0.1 and call that -1. These just represent the factors of 10. I can also make a plot where I use this as my basis. So I'm comparing really big and really small numbers. And I'll show you some examples of that coming up. That's how logarithms work. We can do this with time scales. We'll start in the middle here with a second. Then we're going to have really fast stuff down here, really slow stuff down here, or long periods and short periods. And again, this is factor of 10 down, factor of 10 down, going this way, factors of 10 going up, and about a factor of 1,000 goes 0, 1, 2, 3. That's what about a factor of 1,000 looks like. From about that line to about that line is about 1,000x. And we can do that all up and down this thing. So that's what 1,000x looks like. Oh, not good. I think I'm still okay. So that's how we can rationalize things. And I'm not going to spend much time on this. Just to say, here's an atomic vibration period. Oops. Here's an atomic vibration period down here. This is, kind of shortest resolvable instant, about 1,000th, or rather about 100th of a second. And in the lifetime sits here, trees are here, and then things like lifetime of the galaxies and all that is up higher. It's an interesting way of thinking that I'll make that we will use a couple times as we go through this process. Length scales, we can do the same things. My basis here is 10 to the 0 is at a meter. It's about, people are about 2 meters tall. Buildings are up here. And the interesting thing is atoms are way down here. That's kind of our building blocks. These cause clusters in aluminum that make them strong. The thickness of metal is maybe 10,000 times the thickness of those diameter of those clusters. And again, we can go here from really small to really large here. And again, if I do really, I could do size of the Earth and size of a galaxy, and we could keep going way up here. Down here, it's difficult to go too much smaller than a proton, but you could. And there's a great IBM movie I'll talk about at the end here too. We can do that with. Well, anyway, here's an example of how this can be used. A couple books that make this point really clearly about how the world gets better all the time due to due to innovation piling up on it. One is Ray Kurzweil has done something that's really brilliant that I'll go through here. Another, there's a guy that made a book called The Rational Optimist. It's called Seth Ridley. They both make the point that things are getting better all the time because we're getting smarter and we have these things working together. So anyway, let me start on this log scale. Here's time before present. This is 1 year here, 1 year before present, or rather 10 years before present, 100 years, 1,000 years, back to here's a million years, here's a billion years, here's 10 billion years back here. Well, life began almost 10 billion years ago, single-celled organisms, and then it went from there to multi-celled organisms, and that took on the order of 1 billion years. So this is time to next event. And then we can look at something that happened more recently. We went from human ancestors to work upright to spoken language. This happened about 1 million years ago, and that only took about 1 million years between events. You can look forward. The Industrial Revolution happened about the 1800s, a little over 100 years ago. And time to the next big event is about 100 years. You get radios, and we get computers, we get internet, personal computers. The point that Kurzweil is saying is all these really significant events, and these events, by the way, came from big thinking historians asking them, well, what are the really big things that happened over all these years? They listed these things down. Kurzweil put them on these log plots, and boom, these linear relationships come out. What this all suggests is that things really are going faster. The world is going to change at an ever-increasing rate, and your students need to be ready of it. If you're going to be part of it, you've got to be literate with all this stuff, and that's part of what we're doing, and it's going to come. It's going to come, and it should be better, but we still, as a species, could screw it up, right? So that's it. So back to materials properties. Let's put all this log stuff into the guise of materials properties. Properties are a way we can talk about fitness for a given purpose. What's the acoustic properties of something? Does it damp or does it ring? What are the mechanical properties? Atomic and chemical. Is it reactive? Is it corrosive? Does it conduct electricity? Does it conduct heat? These are things we can all talk about as properties with numbers. We've talked about that before. Some properties we can change easily. Good example of that is strength. Some properties we can't change very easily. Good example of that is density. Density, D-E-N. For example, all aluminum alloys have about the same density. All steel alloys have about the same density, but we can vary their strength all over the place. We'll talk about how that's done later. So I want to consider two materials properties that changed a lot through history and how they changed through history. One is strength, and again, I can call strength, S sub B is sort of a breaking strength, and we do this basically, again, talked about this before. We make a wire, have some cross-sectional area associated with it, A, put some force on it, find that force at which it breaks. The breaking strength is basically force over area, and that have dimensions associated with it. Those dimensions might be newtons per square meter, and we call that thing a Pascal. Or we could do density. For example, we've got a cube of something, and this cube has some mass associated with it. We can also measure its volume, and then density. We usually give it the symbol rho is just equal mass per volume. It has units, for example, of kilograms per meter squared, or possibly grams per cubic centimeter. Okay, so we have a whole bunch of materials out there, all kinds of materials. Let's consider the kind of the universe of those materials, and a guy, Mike Ashby at Cambridge University, did an amazing job of this. He's done some amazing things overall, and I'm using this from his work. But he's taken all these materials that existed back in 50 BC when Great Uncle Ugg was running around. These are natural materials, ceramics and glasses, metals. This is pretty much what you had to work with: rocks, bones, metals that we might be able to refine. And you can see what was there. We had kind of modest strengths. Strengths would go up here in these units up to about 500 or so megapascals. I mentioned pascals before. And then also this is the range of densities available. Metals are pretty dense. These natural materials were not so dense. And this is if you're going to design something back then, these are all the materials you had to pick from, and that's what limited the design that Uncle Ugg could make things with. So he could make things like hammers, sort of, and maybe some simple axes and some daggers, and that's about all we could make. And we didn't have interesting electrical properties and all that. That came much later. Look, go to the materials that we entered World War II with. We have a few new things. We've got ceramics and glasses have entered the scene. We've got polymers and elastomers that are there. And then also you can see that where our strengths were limited before, about here, we're getting a factor of 2 or 3 greater in strengths. There's a wider range, and there's more you can pick from. That's why we were able to go from things like handheld axes to making aircraft and tanks and things like that. And if we go backwards, you can see the increase in filling in that space. If we fast forward to today, we see again our highest strengths back in 1945 were around here. We have stuff that's about 10 times as strong. We have ways of processing it. We've got much wider range of densities, not so much greater on the high side, but on the low side we have all these foams. We've got natural materials, polymers and elastomers. Composites are fairly new on the scene. Done a lot new with ceramics. So again, quantitatively we can see what's gone on, and all of these new materials enable new designs. This is why things keep going faster. All these new inventions we have compound on one another. You invent a material that allows us to invent something else. It all works together. That's why the world is speeding up. Kind of cool stuff, I think. So anyway, challenge you can do with your students. Think about some engineered device that's been around a long time. Maybe a shoe, a sewing needle, something for playing music, crutches, you name it. And think about the materials that were available back when versus those that are available now versus what might be available someday in the future. I think this could make a really good, compelling exercise to see how these things fit together, how design, properties, materials, and technology all fit together. It's a good possible assignment, and I'll let you flesh that out on your own. Other directions you can take with this kind of content, hopefully. Math, please consider teaching logs. It's really not that difficult. It's a distinctive thing. Lots of college STEM grads don't necessarily have this. It's great for making big comparisons, and there are things that we have to compare where it's mind-boggling how different things can be. A second thing you might think about is really what does enable the future? Where are the challenges and opportunities? How do new materials and all fit into this? I think this area of applied history is an interesting one, and this is sort of a quantitative way at it. Then lastly, I'm going to plug one thing that was an absolutely brilliant movie at the time. There's a 1977 movie put on by IBM called The Powers of 10. There's a YouTube, and it just goes, starts at a picnic and goes out 10 times, out 10 times, out 10 times. Before long, you're looking at the Earth, then you're looking at the solar system, then galaxies, and you can see that there's all this structure going up, and there's also all this structure going down as you go into materials. So that's that. I'm going to leave you there, and look forward to seeing you more on the internet. Take care.